Hi, in this video I will go over a Leetcode problem called twosum. So we are given an array of integers called nums and also given an integer called target, and we want to return the indices of two numbers such that they add up to target. Also in the problem statement it says you may assume that each input would have exactly one solution and you may not use the same element twice. Now let's look at an example. Say we are given an integer array of 2, 7, 11, and 15, and target equals 9. Then so we want to find two numbers, right, that add up to our target number and then return their indices. So we have 2 and 7, and then we want to return their output as an array of their indices, so 0 and 1. And it says that it can't be the same element twice. So for example, if our target was 4, it cannot be 2 plus 2. And another thing is that there's only exactly one solution, and the order of our output doesn't matter if those were switched. Like if we had 1, 0, it would still be a valid solution. Right, so first thing I like to do is look at the inputs and output. So we are given an integer array which is not sorted, integer array. And we want to return also an integer array of just 2 elements. Right, so some ideas I had were like, what if we sort the integer array, then basically finding the target would be faster instead of like going through every element, because the brute force approach would be to have a for loop that would iterate through every element, and then a nested for loop that would iterate through every element and compare it with the outer for loop element. So for example, we start with 2 and then compare it with 7, so 2 plus 7, that's 9, and then we return true. But if our complement, which is 9 minus 2, so 9 minus 2 equals 7. This is the complement. If our complement was somewhere here, then we would have to iterate, and in the worst case, it's n squared, right? So this is our brute force solution. It's not very efficient in terms of time. It's O of n squared again. But then if we sort this, we can assume that sorting takes big O of n log n in C++ without taking any space for the sorting function. Well, if we have it sorted, then what if we do a binary search trying to find the complement, right? So in this case, this is sorted, but let's say we start in the middle, right? We start at 7, and then 9 minus 7 is 2. Well, then we move here, and this would improve our time complexity to n log n without any additional space, except for the return output, of course. So this was like my initial idea after the brute force, but then I wanted to come up with a linear time complexity, right? So that's the best we can really have, because we do have to go through every element at least to find the complement. So applying binary search, although it's log of n, we would still have to sort the array, which would take n log n, and it would take over the binary search feature. So we would have to trade off with the space complexity and use like a data structure. But before we do that, I'd like to think about some edge cases and constraints for every problem. So edge cases plus constraint. Okay, so first thing we're gonna assume like basically the solution exists. Alright, there are two numbers that are gonna add up to the target, and then we're only gonna be given integers. Negative to positive is fine. And what other edge cases do we have? Yeah, I think that's pretty much it. And the array size should be at least 2 elements, right? So array size greater than equal to 2. Yeah, because we cannot add the element itself, so it has to be at least 2, right? Okay. So next thing is to think about like the optimal solution. Let's see. So optimal solution, and I'll keep this test case here just so that we can refer back to it. And a second. Yeah. So the test case was 2, 7, 9, 11, I believe, with a target. Oh, yeah, with a target equals to 9. Okay. So let's say we use a data structure. Well, we want to use a data structure that is efficient in search, right? Efficient in finding. Because if you think about it, like, we can use the target and then go through this list, and then based on our ith integer, we can have this complement that we can look for in this map, which, I spelled it, but it's going to be a hash map because it would only take big O of 1 to find an element, which is efficient, and we would only have to iterate through the array once. That makes sense, right? So let's look through an example. Let's say we had our map. Initially, the map is going to be empty. And then as we go through the list, we're going to have 9, always the target. So 9 minus our first element, 2. This is going to be equal to 7, right? We look, is 7 in the hash map? Well, no, it's not. So what do? Well, we're going to add the value itself, not the complement. Because if we add this value and then it is a complement to another number, then it must be in the map here. So, we just need a set in this case, right? Because elements are going to be unique. And we don't really have, or no, actually we have to use a map to keep track of the index, because that's where we're going to return. If our output was just a Boolean, then we would use a set. So 9 minus 2, right? And then in our first iteration, we add 2. And then with its index, that's 0 as the value for this key. Next, we're at 7. We do 9 minus 7, well, that's 2. And then we check, is 2 in our map? Yes. So what do we return? Well, then we create a new array, and we take the value of the complement, so 0, and then we take the index of our current number, which is 1, and we return that in our output. So here's what the solution is going to look like in C++. Yeah, I'm going to add this over here. Okay. So first thing, we have the function. It's called toSum, right? It's going to return a vector, which is going to be of size 2, basically, the 2 indices. And it takes in nums, which is an array, or a vector in this case, and an integer target. So Here's my solution. First thing I did, I initialized a vector called toSumIndices. So this is going to be our output result. Initially it's empty, right? And then we have an unordered map called numsMap. It's going to have integer keys and integer values because our input is just ints. It's just ints, right? So it's also empty. And then in one pass, we're going to do everything basically. So we have an for loop. Every time we start this for loop in a new iteration, we recalculate the complement, right? So in this case, complement is target minus the current or element at the ith index. In our example, we had so 2, 7, 9, 11. So in our first iteration, it's gonna be, our complement is gonna be 9. That's the target, right? And let me just write this down. So target equal 9. 9 minus 2, because this is our first element, and we're gonna have 7 as our complement. Next, what we do is look in the map to find if the complement, which is 2, exists, right? This is basically saying if the complement is not in the map, this is how you do it in C++. If it's equal to the n means it doesn't exist. Well, then we insert into the map the element and its index, like how we did over here, right? The element and its index. The element is nums of I and its index is just I. Otherwise, if it's found, well, we just have to push 2 things into our output, the toSumIndices. What are those 2 things? We first push the numsMap complement because it's in the map, right? So we kind of like index into it to get the value, which is going to be 0, the index. And the next thing we push is the current I index, right? Because this is the one that we found a corresponding complement to. And our output would be 0, 1. And we return that. If, I just have the return at the end here, so if this wasn't found, then it would return an empty array. But the question tells us to assume the solution is always going to exist. And yeah, finally, this is going to be big O of n for runtime and big O of n for space, because we're using an unordered map, and then we have a vector which is of size constant. It's always going to be 2, so we can just assume it's going to be big O of n.